Hello, geometry students. Here we go. We are on to 11.6. A couple more lessons left in chapter 11, and we're nearly done. This is on segment relationships. And well, all I can say is it's going to answer all the questions you never had about lines and segments with circles. So here we go. Let's jump right in. We got 3 definitions and then just some practice problems straight from the book. So let's look at some definitions. And again, each one is going to provide a way of solving segments and lines related to circles. So the first one is called the chord-chord product theorem. And so what we have here is we have a circle with 2 chords. We have chord AC right here, and then we have chord BD right here. And these kind of look like diameters, but no, we're talking about chords. So these could be any line that goes from one edge of a circle to the other. And when you have those 2 lines and they cross at any point, they're not crossing in the middle, but at any point that they cross, they have a multiplication or product theorem. And that is AE, so this piece of this chord, times the other piece of this chord is equal to the product of this piece of the chord times its other piece. Okay, so as it says there, so the purple AE times the red CE is always going to be equal to BE times DE. Okay, so let me just, even if it looks something more like this, I'll just draw another circle. Okay, if I have a chord here, whoops, fix that. If I have a chord here and here, the product theorem would hold true that this piece times this piece would be equal to this segment times this segment. Okay, and so that allows you to find distances within circles fairly easy. We'll do some practice problem just like that. Okay, so let's look at another one. This is called the secant product theorem. And so now we have not chords from edge to edge, but a secant that's passing through the outer line of the circle. And so the way that this product works is similar to the other one, but not quite. It is basically says that the product of the entire chord, A to E, times the segment of that secant line, sorry, I said chord, secant line, the segment of that secant line, which is outside the circle, is going to be equal to the other line's entire distance, the other secant's other entire distance times that smaller segment that's outside the circle. So again, looking at the letters specifically here, AE times BE is always going to be equal to CE times DE. Alrighty, and so it's not the pieces, it's not AB times BE. That's an easy mistake you could fall into, but it's the entire distance here times then the, oops, that looks terrible, times the distance outside the circle. Okay, times, again, let's get a better color, this entire distance times the outer piece right there. Okay, again, terrible. Alrighty, and we'll do a practice one just like this. So that's secant product theorem. One's with chords, the other one's with secants, and then they throw a nice little combo at you, secant tangent theorem. And again, just a wonderful situation that I'm not going to throw any word problems at you at this point, but are applicable. And you have a secant line such as DB there. This is our secant line right here. And then you have a tangent line right here. And so if you ever have that situation, then it is similar to the secant formula. It is the entire secant line times the amount that is exterior to the circle, draw my brackets very well, is equal to the tangent line squared. Okay, and so you see here, DB is equal to, times CB is equal to AB squared. Okay, so the tangent line, which we haven't seen before, so remember that's if that helps, we're going to follow a pattern that we haven't seen. That's going to be AB squared. So let's look at some questions and see this in action. We got one of each type plus a bonus one, and kind of a more nuanced one, number 5, that we'll look at. But this is right out of our book, doing 2, 5, 8, and 10. Number 2, let me find the page. We simply have to find the variable. We have you can see these are chords, so we're going to use the chord-chord product theorem, and we have to find y. Y doesn't look very good in this particular case, but there's y. So I need to find this distance right here. Well, according to the chord product theorem, the two pieces, it's almost like ratios or proportions. I can say that this part times this part, 4 times y, is going to be equal to, change colors here, the other two dissected pieces, or we'll say dissected pieces of the chord, 3 times 8. And so in a way, you are setting up kind of a proportion. 4 times y equals 3 times 8. So then we can simplify that to 4y equals 24. And then we can divide by 4. And we can see that y equals 6. Let's see, that problem only has find the value of the variable and the length of each chord. Okay, so there's the variable. And so what are the lengths of the chord? Well, so the red chord is simply going to be 4 plus 6. So it is 10. And that would be chord LM. And then for the ones in green, we already see 3 and 8. So that's just 3 plus 8. So it would be 11. And that is chord HJ. Okay, so pretty simple. The two pieces of one chord multiplied should equal the other two pieces of the other chord multiplied. And this can get a little more interesting when we move on to a question like number 5. I've drawn some of the word problem picture here. But it says a section of an aqueduct is based on an arc of a circle as shown. EF, right here, is the perpendicular bisector of GH. Okay, so that means perpendicular bisector of GH. GH equals 50. So I know that this piece right here is 50. And EF is 20. So this piece here is 20. What is the diameter of the circle? Okay, so you've got this is part of a much larger circle here. That's not a diameter. GH is not the diameter, but we can use this to find the diameter. Why? Well, because let's imagine the rest of that circle for a moment. And we can see that EF, I changed colors, EF is the continuation of a diameter, or EF is the start of a diameter. So what we're really looking for then is this other piece right here. Because once I know that section, we could go ahead and call this something like FJ. Then we'll know the entire diameter. So can we use the chord product theorem? Well, let's see. Do we know G, F, and FH? Yes, we do. If the whole thing is 50, then that means this must be 25, and this must be 25. So we can start that off. 25 times 25 has to be equal to 20, which there is EF, times this piece right here. Okay, we'll call that X. Okay, so 20 times X. Okay, and then once we know that X, we'll be able to find the actual diameter. So 25 times 25, that's going to be 625. Oops, looks bad. Equals 20X. And then we just divide both sides by 20. And so we get X, cancels out, X equals 31, so check, yeah, 31.25. Let's read that better, sorry. 31.25. Okay, so that means this piece right here is 31.25. So that's not your final answer though, because again, it asked for the diameter. So I have to go back and say, okay, so that would be 31.25 plus EF right here, which is 20. And so the entire diameter would be 51.25, and we're dealing with feet. So let's not have any naked numbers. Let's put our units on. 51.25 feet. So the key to this one is realizing that, first of all, when you have that perpendicular bisector and they give you GH, you can know your two segments. You can know that they're both 25, so that allows you to use this product, or this chord product rule. and then we find our missing x. Okay, let's move on to number 8. Now we're dealing with secant lines, so we're going to want to use our secant product rule. And so we can see we need to find x and then the missing secant segments, or the full lengths. So let's go ahead and apply it. Again, it's the entire, change colors again. It's the entire line times the amount piece of the line that's outside the circle. So that entire line is 20.7, 10.7 plus 10. So 20.7 times the part outside, which is another 10, equals, same thing at the bottom, the entire line, which in this case, oops, I'm going to need a little more room. Let's rewrite this. Let's do it right here. 20.7 times 10 equals x plus 11.5, because that's the entire line down there, that's L to G, times then the piece that's outside, and that's my 11.5. Okay, so now we just need to solve for x. Well, 20.7 times 10 is 207. Beautiful penmanship. And then we could distribute over there, but don't. Just say it simply don't. Because watch, you just do x plus 11.5 times 11.5. So now let's just divide by 11.5 on both sides. That cancels out. Okay, and so we get 18. 207 divided by 11.5 is 18 equals x plus 11.5. So now we just need to subtract 11.5. And so we're left with x equals, what is that? 6.5. Okay, so there's my x. All right, and then in order to find my other secants, well, the JG is really easy. We already did that. So JG is equal to 20.7. And my LG, this LG phone, is equal to 6.5, which is what we just found, plus 11.5. It takes me back to my 18. Okay, so there's my two secant distances as well as my x. Now it's a little more complicated because you have that addition fact that you're going to add the chord plus the piece that's outside. And so the solving of these is a little more complicated looking, but you can see it's just a matter of setting it up. You divide and subtract. And we'll see number 10 is somewhat similar. Number 10, though, now we're going to be using the secant tangent product theorem, okay, where we know that the entire secant times the outer piece is going to be equal to this tangent line up here squared. So let's set that up. The entire secant line would be y plus 3 times just the outer piece, which is 3. If you wanted to distribute that, you could, but I'm not going to. I think it's simpler. Equals 4 squared. Okay, so then that would just change to, we rewrite that, y plus 3 times 3 equals 16. We can now go ahead and just divide by 3. I like to change colors when I do my algebra steps. And so now we have y plus 3 equals 2. Oh, I'm sorry. Yeah, somebody stop me, please. We're still in time to fix it. That's why you show your work. 4 squared is not 6. I don't know where that came from. 4 squared is, I didn't finish my thought, is 16. There we go. So we get y plus 3 equals 16 over 3. Okay? And then we go ahead and just subtract 3 from that, from both sides. But you can crunch that number. Let's see, that would be 3 times 5. Yeah, so that'd be 5 1/3 if you want to put that in a fraction. And then we subtract 3 from both sides. Okay, from both sides. And so then we get y equals 5 1/3 minus 3, we get 2 1/3. Okay, you could put that in decimals. I didn't because you can't round a third accurately or completely in 5 point or 7.5.33333333. So 5 1/3 minus 3 gives you 2 1/3. So your y there is 2 1/3. Let's see, do we have to find anything else? No, just find the variable. So there we go. 2 1/3, also known as 7/3. Any of those things work. Don't be afraid of fractions. You can do it. All right, so those are the chord product theorem, secant product theorem, and the secant tangent product theorem. Praise the Lord. We'll see you in class. We'll have a good time.